Hi, in this lecture we started to discuss software testing and why it is important to do it and why we need to do this in a rigorous manner. Well, because it costs money and time from people, right? But before we saw ways to do it, we discussed a bit of terminology because we use many different words like error, mistake, defect, bug. They are not the same, they have different meaning and this helps us to communicate. So a failure is when the software behaves in a way that we were not expecting it to behave. For example, when you have the blue screen in Windows, this is a failure. We were not expecting this, but this was what the software did. So this is a failure. It's more from the external perspective, right? Um, a failure is caused by a bug. So a bug is a small problem that we have in a component, in a function, which caused which caused the software to behave incorrectly. For example, an if instruction that was wrong, right? So in a way, we can try to see this the other way around. So a bug happens, and if the buggy code is executed into production, this bug will become a failure, right? And defect, bug, and fault, they are all synonyms. I showed you an example. So this was from Apple's SSS layer. There were two go-tos. This is a bug. And finally, the mistake. The mistake is the human action that produced the incorrect results. So ourselves as developers, we do mistakes. These mistakes, they are usually reflected as bugs in the source code, so incorrect statements in the source code. And if this bug is executed in production, this will become a failure. These are three important terms that we have. Two more, validation and verification. Also important in software testing because validation is more focused on are we building the right systems? Are we building the software that our user wants us to build, right? And if you think about user stories, this is more like the acceptance criteria. And acceptance criteria, they help us to validate our software. But we also have verification, which is about are we building the system right? So does it work? So we have this implementation. Does it work? In the agile part of the lecture, we discuss validation a lot and how user stories can help us on this. We're going to focus a lot on verification now. Cool. So now let's think about practices, techniques to test software. And one thing that I want you to notice is that as software testers, we look forward for systematic ways to test software. We want to find ways, techniques that we can just systematically reproduce, and those techniques, they should be able to review the bugs in our system, right? And we can see this from different perspectives. So one of them is I want to test my software, and what I have is a specification, so requirements or more formal models, and this is the input I use to come up with tests. Or I can look to the structure of my software, for example, the source code, and from there I try to come up with tests. In this video, we're going to focus on the specification-based testing, right? And I gave you a problem. So we're working for this chocolate factory, and we need to calculate the number of packages we should produce for a given number of kilos of chocolate we need to produce. So read the requirement. And then what we try to do is, based on these requirements, we try to come up with representative classes or different partitions in that requirement that would that need to be tested, right? So for example, I can see that I have some keywords in there like small bars, big bars. I always use one before the other. This gives me insights on what to test. And from this requirement, I saw a few different partitions. For example, what happens if I only have small bars, if I have only big bars, if I have a mix of small and big bars, not enough bars. Maybe an invalid numbers, this can be not from the specification, but I know I have to test for invalid numbers. So this is what we call partitioning. So I look to a specification and I try to break it down into unique representative classes, meaning if the program receives as an input one specific class, for example, only small bars as an input, my program will behave differently than if it received only big bars as an input, right? So I'm trying to find the different partitions that would make my software to behave in a different way. As soon as we do this, we try to come up with concrete cases that would represent that partition for us. For example, if I need big and small bars, maybe small 5, big 3, total 17 can be a possible input for this partition. And this is in a way known as the category partition method. So we try to identify the parameters or the inputs that we have, then the characteristics of each parameter and how they can influence my software. A lot of them come from the specification. Some don't come from the specification, but I can use my knowledge as a tester. And then I just combine them all, right? And I do all the tests that I can, but maybe this number is too big, so we try to minimize the set of tests. For example, I don't have to test maybe all invalid combinations. Maybe just one invalid combination is enough, right? So for example, I have as an input there small, big, and total. Maybe I just test one invalid combination for small, and I don't have to combine it with everything else. And then I generate all the combinations that I want to test. Then I went to another concrete example. So we are offering a discount during Christmas. If it's Christmas, we have discount, not Christmas, no discount. Again, I try to look for keywords in the specification that would help me to review the partitions. And then the two important variables that I see there, date, raw amount, Christmas, not Christmas, for the current date, and then for the raw amount, positive number, 0, negative number, and I just combine them all, right? Negative number is an exceptional case. I will mark this, and I do all the combinations. Christmas with positive number, 0, negative number, not Christmas with positive number and 0. This is the category partition method. So some definition for partitions. Partitions are representative classes of our program, and they guide me throughout the testing phase. Then one small discussion that we had is, if we see partitions as pieces in a puzzle, but I have to choose one concrete implementation of that partition, which one should I pick? And it kind of doesn't matter. We call this equivalent partitioning in a way. If the partitions are really unique, whatever concrete point you pick from there is enough, right? Any case should be a good representative for that partition. And of course, we try to just test one case per partition because we want to reduce the cost, right? Tests cost money, and we want to do the smallest amount of testing possible, right? I gave you another example for you to try. And then what we noticed is, well, even though we thought a lot about partitions, there were still bugs in there. So are partitions enough? Well, this is the bug, but partitions, they do help us, but the problem is that sometimes we need to think about the boundaries, right? We write lots of bugs in the boundaries of our partitions. So if we think about our tests as pieces in a puzzle, we should test the connections. So where one piece becomes the other. We have a boundary in there, and it's quite common to write bugs in between them. So for example, this is one boundary. If I have small 2, big 3, total 17, I can see that when it's small is 1, that's not possible, but then when small becomes 2, that is possible. So this transition from small 1 to small 2 represents a boundary in my partitions, and maybe I should test if this transition goes smooth. So having a test with small 1, big 3, total 17, and then small 2, big 3, total 17 can be nice because it's going to test the boundary. So this is boundary testing the boundaries between our partitions. And then I just showed you lots of boundaries we can test in this chocolate problem. And then as soon as we had this, we started to discuss boundary analysis. And this is just a different way to see how we can test the boundaries. So for example, let's suppose you have this condition in your program, x greater than or equals to 100. As soon as I see this condition, I can think about 4 different things. So the first one is what we call the on point, and the on point is the number that is in the condition. So 100 is in there, so 100 is my on point, right? And then this makes me think about what happens if x is 100. In this case, 100 is greater than or equals to 100. So the on point makes the condition to be true in this case. Then I have in points. And in points are points that are where it is evaluated to true. For example, 101 would be evaluated to true, 102 would be evaluated to true, and etc. So on point is the point on the condition. In this case, it makes the condition to be true. In points are points where the condition is true, right? That makes the condition true. The other way around, I have the off point, which is the first point that makes the on point to flip. So on point makes the condition true, the off point would make the condition false, and it's the first point makes the condition false. In this case, it's 99, right? And then we have out points, and out points are points that make the condition to be false. If I switch this again, x greater than 100, so no equals anymore. Now I can see that the on point, 100, still 100, but at this time the on point makes the condition to be false. So an on point is now part of the out point, right? Now the off point is, it inverts the result of the on point, so on point is making the condition to be false. The off point is the first point that makes the condition to be true. And the off point in this case is part of the in points. So more formally, the on point is the one exactly on the boundary. The in point makes the condition true, the out point makes the condition false. The off point flips the outcome of the on point, and it is as close to the boundary as possible. And what we want to do is to test these points, right? And make sure that our program behaves correctly when we are in the on point, when we are in the out point, because they are the boundaries. And then we discussed what to do if we have multiple boundaries, right? So I have two conditions, x greater than 10 and y smaller than 100. What do we do? And I introduced you the simplified domain testing strategy, and the idea is that you're going to look to each of the conditions independently. For each of these conditions, you're going to have two tests, one for the on point and one for the off point. And for the other boundaries, you have to pick values, right? Otherwise, it doesn't work. And then you just use varying in points for the remaining boundaries. And you can see this in the domain matrix. For example, that's the condition, x greater than 0, and x is smaller or equals than 10, and y greater than 1. I know that for each condition, I have three conditions in there. So x greater than 0, smaller than 10, and y greater than 1. So I have three conditions to test. And for each one of them, I'm going to have on and off points, right? And for the others, just typical varying in points. So for example, for the first one, test 1 would be the on point for x greater than 0. The on point is 0, right? The number on the boundary. And 0 makes the condition false. So the off point is the first one that makes the condition true, which is 1. So I have my values for x. Now I need values for y. I just picked any random in point. So 10 and 16. So 10 and 16 are in points because they all make y to be true. I just tested the first condition. I go to the second one. So the on point for x is smaller than or equals to 10 is 10. 10 makes the condition to be true. So off is the first one that makes the condition to be false, which is 11. Then some in points for y, 109.3, 2000, whatever. And finally, to the third condition, 1.0 is the on point, and the off point is the first one that makes the condition to be false, so 0.9, for example. And then some typical in points for the x, 4 and 6. Then I try to motivate you to do boundary testing, and research shows that students don't do boundary testing that much. They focus a lot on happy paths, so only, the simple path. But you should think about boundary testing, okay? We want to automate it as much as possible. I introduced you to PyTest. We discussed this in another video. I'm not going to dive into it that much. And finally, we discussed a little bit more of a formal model. So requirements are usually informal ways of describing the specification. If you're using agile user stories or UML, well, use cases can be quite informal. But if we have more formal methods, more formal models, we can have better tests as well. For example, If we think, and I gave this KPN example, if you have many different choices to make, are you a new or a node customer? You want to sign it off for 12 months or 24 months, etc., etc., etc. Then we can really try to think about decision tables and really build a decision table that contains all possible outcomes. For example, if you're an international customer and if you want the auto renewal activated, then that's the price we get. So if you have those decision tables, they are more formal, right? Because they give us all the possible inputs and outputs. Then I kind of know what to test. I give you some example with sometimes you don't care about a value. For example, if international is false, then loyal is also false, then the auto renew we don't care. But we can try to expand it, right? And remove duplicate. So at some point we can see our big model becoming a smaller model so that we can test. In the next lecture, I'm going to discuss MCDC, and you can try to think about applying MCDC criteria to these tables. But what I want you to see from now is that this is a bit more formal than just a specification, and this can guide me through my tests. Or I can think about diagrams that can represent states of my software. For example, let's go to a concrete example. This is a withdrawal application, and then the software starts, the card inserted, then this means we have to wait for PIN. The user enters the PIN, it goes for the first try. If the PIN is okay, we can access the account. If it's not, you go to the second try. So you see that we just found a way to represent our requirement in a more formal model. And this is quite nice because as soon as I have this, I know what to test, right? I just have to test all the possible paths in this picture. There are different ways you can represent these pictures. I'm not gonna dive into this in the video. Together we tried to draw this state diagram for the car radio. So you're in the radio. If you go to MP3, then it goes to the MP3 feature, and so on and so forth. And what I want you to see is that this gives us input to test, right? We know that we need to test all these transitions, for example. If you move from the picture to a table, this table tells us what to test, right? So I can test all the events that I can see that, for example, if I'm on radio and I press MP3, I go to MP3. If I'm on MP3 and an alert happens, I go to traffic MP3, things like that. So I can test these transitions, but I can also test the empty cells to make sure that my software doesn't have a bug if I try a transition that is not valid. If you try to expand this table into a tree, so I start in any state, for example, radio, and then I try next, I try alert, I try MP3, and then I keep expanding this tree, and I stop whenever I see something that I saw before. For example, I started in radio. If I see radio again, I can stop, right? Because then I would start repeating the same tree. If I try to expand it, I now know all what I should test, right? I just need to test all the paths. Things to think, does the event trigger the right condition? Does it lead to the correct state? Does the event invoke the correct action? Do we have some history sensitivity bug in there? For example, if I go to the same state twice, maybe it doesn't work. Are there extra unspecified events? So having a state machine helps us to think about those things. To summarize this video, because we discussed lots of stuff, we started with functional testing and mostly based on the requirements. And to see a requirement and then think about tests, we talked about the category partition methods. So we saw how to break our requirement into testable things, elements. We saw that boundaries are important and we should test for the boundary. And then we saw that if we have some more formal model, like a state machine, we can also derive tests from there. That was the lecture.